Welcome, everyone. Thank you for coming to the One World seminar on the mathematics of machine learning. It is my great pleasure to welcome Gal Vardi from the Toyota Technological Institute in Chicago and the Hebrew University. If you've got questions, feel free to put them in the chat or to unmute yourself. If you unmute yourself, you will be part of the recording. If you prefer not to, put it in the chat and somebody will ask the question on your behalf. And without further ado, Gal, the floor is yours.
Thank you very much. And thank you for the invitation. I'm very happy to be here today. And I will talk about implications of the implicit bias in neural networks. Okay, so I will start by explaining what the implicit bias is. Neural networks in practice are often over-parameterized, which means that the number of parameters in the network might be larger than the number of examples. And in such networks, there are usually many possible solutions that fit the training data set. It means that there might be many possible neural networks that we might converge to. But in practice, it seems that gradient methods tend to converge to networks which also generalize well. So from the set of all possible neural networks that fit the training data set, some solutions also generalize well on unseen data, but most solutions do not generalize well and only overfit the training data. But for some reason, it seems that in practice, there is some kind of bias towards the solutions that generalize well. And this topic of understanding this implicit bias was studied extensively in recent years, and it is believed to be key for understanding generalization in deep learning. Okay, so in this talk, I will discuss 3 papers which are related to the implicit bias. And in all 3 papers, I will discuss implications of the implicit bias. In the first part, I will discuss a paper about generalization in univariate networks, which is a joint work with Itai Safran and Jason Lee. And then I will discuss a paper about reconstruction of training data from trained neural networks, which is a joint work with Niv Chaim, Gilad Yudai, Ohad Shamir, and Michal Irani. And finally, I will discuss a paper about adversarial robustness in neural networks, which is a joint work with Gilad Yudai and Ohad Shamir. And all 3 papers will appear in NeurIPS in November or December. Okay, so as I said, the implicit bias was extensively studied in recent years in many settings. And I will not even try to discuss all the known results for the different settings. I will just focus here on one specific setting. And this will be the setting that we will consider in all 3 parts of this talk. So we consider fully connected ReLU networks, which are denoted by phi theta x, where theta are the parameters of the network, and x are the inputs. And we will consider training the network with gradient flow, which corresponds to gradient descent with an infinitesimally small step size. And we can think about it as an approximation for gradient descent with small step size. We'll consider classification, so the labels will always be in the set plus minus 1. We will train the network with respect to the logistic loss, which is also called binary cross entropy. And we will need a few definitions. First, we say that a network is homogeneous with respect to the parameters if by multiplying the parameters by some positive constant alpha, it is equivalent to multiplying the output of the network. So changing the scale of the parameters only changes the scale of the output, but does not change the structure of the function computed by this network. And the important thing to know about this definition is that it holds in fully connected radio networks, as long as there are no bias terms in layers other than the first hidden layer. So for a network, in order for a network to be homogeneous, it is okay to have bias terms in the first hidden layer, but it is not allowed to have bias terms in the other hidden layers. Also, we say that the gradient flow converges in direction to some theta tilde if, as the time t goes to infinity, the direction of theta converges to the direction of theta tilde. And an important thing to note about training networks with the logistic loss is that the logistic loss never gets value of exactly 0, because it is always strictly positive. So in order to converge to 0 loss, the output of the network must go to infinity, which means that the parameters diverge. The norms of the parameters go to infinity as the time tends to infinity. But since we will consider homogeneous networks, then we will not really care about the scale of the parameters. We will only care about the direction of the parameters, because only the direction is important for the structure of the function computed by this network. Okay, so this is the setting, and we will use throughout this talk, we will use this theorem. So this is a theorem by Luan Lee and Jean Telgarsky. And it says that in homogeneous Rayleigh networks, if gradient flow reaches some small training loss, then it converges in direction to a KKT point of the max margin problem, which is the problem which is stated here. This problem says that considers minimizing the norm of the parameters under the constraints that each example is labeled correctly with margin of at least 1. Okay, so the constraints are that yi phi theta xi is at least 1. So the margin is at least 1, and we want the norm of the parameters to be, the L2 norm of the parameters to be as small as possible. Now, okay, so the theorem guarantees convergence in direction to a KKT point of this problem. A KKT point is the first order stationary point of this optimization problem. And it is an extension of Lagrange multipliers, because in Lagrange multipliers, we are only allowed to have quality constraints. And here we have inequality constraints. So the KKT approach is an extension of Lagrange multipliers. And more formally, the definition of a KKT point is a point that satisfies these KKT conditions. Now, the KKT conditions are given by this set of equations. We will talk a bit more about these equations later, but for now, all we need to know for now is that a KKT point is a point that satisfies these equations. And also an important thing to note is that it was shown that these conditions are necessary for optimality, but not sufficient. It means that it is possible that gradient flow converges in direction to a KKT point, but this KKT point may not be an actual optimum of this problem. So the theorem does not guarantee that we actually maximize the margin. It just guarantees that we converge to a KKT point of this problem. And intuitively, we can think about this theorem as saying that there is some kind of tendency towards margin maximization. But this is not a formal statement, because it does not always maximize the margin. But intuitively, you can think about it as trying to maximize the margin. Yeah. Okay, so any questions about this theorem, because we will refer to it later. Okay. Now, sorry about the noise. So how can we use this theorem in order to show implications the implicit bias. So there are three possible approaches. One approach is to assume that gradient flow actually finds a global optimum. So we said that it is not guaranteed that gradient flow actually converges to a global optimum. But since the theorem does say that intuitively that there is some kind of tendency towards margin maximization, then we can ask, okay, so suppose that the margin is maximized, what are the implications of such margin maximization? The second approach would be to consider some specific settings, and then to prove that in these specific settings, the margin is guaranteed to be maximized by gradient descent. So in general, we know that gradient descent does not always maximize the margin, but for some specific settings, we can show that it does maximize the margin, and then you can use it in order to show implications. And the third approach would be just to use the KKT conditions, because we know by the theorem, we know that gradient flow is guaranteed to converge to KKT point. So if we just use the fact that the KKT conditions hold, then we don't need any assumptions because it is guaranteed by the theorem. Now, in this talk, we will use this third approach. So we don't have to have any assumptions about margin maximization. We just use the theorem about this convergence to the KKT point. Okay, we'll start by considering shallow univariate networks. We consider a network which is given by this expression. So n theta x is the network with input x and parameters theta. And the parameters are wj, which are the weights of the first layer, bj, which are the bias terms, vj are the weights in the second layer, and in the hidden layer, there is ReLU activation. Okay, so it's a depth to ReLU network. And we assume that the data set is such that each label yi equals to the sign of n star xi for some network n star. So n star is a teacher network, which classifies the data set. And we assume that this teacher network n star is also a network of depth 2. And we denote the width of this network n star by r. So r is the number of hidden neurons in the hidden layer of n star. Okay, so for this setting, we ask two main questions. The first question, which is our focus, is can we characterize the implicit bias? But also another question, which is also important, is about optimization, because a natural question is, does gradient flow provably converge to a zero-loss solution? Because it might be possible that gradient flow gets stuck in some bed local minimum. So we ask two questions. The first is about implicit bias, and the second is about optimization, about whether gradient flow succeeds in converging to small empirical loss. And we will show the following results. I will state it briefly here, and then I will get into more details. So about the implicit bias, what we show is that gradient flow minimizes the number of linear regions up to a constant factor. Note that since we consider ReLU networks, then a ReLU network computes a piecewise linear function. So since we consider ReLU networks, then we can consider the number of linear regions in the function computed by this network. And what we show about the implicit bias is that it minimizes the number of linear regions up to a constant factor. And this is the result about the implicit bias. About optimization, what we show is that under certain assumptions on the initialization, gradient flow converges with high probability to small loss. And then we will combine these two results in order to conclude that gradient flow learns shallow univariate networks, in the sense that starting from this random initialization, it converges with high probability to a network, which also generalizes well. Okay, I will state a bit more formally the result about the implicit bias. What we show is that if gradient flow reaches small training loss after some time t0, then it converges to zero loss and converges in direction to a network with at most all of our linear regions. Recall that R it denotes the width of the teacher network N star. And since the teacher network N star is of width R, then it can have roughly our linear regions. And therefore, the best we can hope for in terms of minimizing the number of linear regions is to have all of our roughly our linear regions. And what we show is that indeed gradient flow will converge to network with our linear regions up to a constant factor. So up to this constant factor, it minimizes the number of linear regions. And note that we consider directional convergence because, as I mentioned in the beginning, the norm of theta tends to infinity as the time goes to infinity. So theta diverges, but we care about the direction of theta because only the direction of theta affects the classification and the number of linear regions. And the scale does not change the classification and does not change the number of linear regions in the network computed by theta, because the scale, if we multiply theta by some constant alpha, it only changes the scale of the output. And it's not important for us because we consider the number of linear regions. Yeah. Now, we can use the fact that gradient flow minimizes the number of linear regions in order to show that it also generalizes well. What we show, note that the result about the implicit bias about minimizing the number of regions is independent of the size of the training set. So it means that we can choose large enough n denotes the size of the data set. So we can choose a large enough n and then use the fact that gradient flow converges to a network with a small number of linear regions, and with standard uniform convergence bounds, we can show that this network also generalizes well. So it means that for a sufficiently large data set, gradient flow is guaranteed to converge to a network which generalizes well. And it means that this result holds for any width of network. So even if we learn a network which is highly overparameterized, so the number of parameters and the width of the network can be huge, much larger than, for example, the size of the data set. Still, this result about the implicit bias guarantees that we do not overfit. So the implicit bias prevents gradient flow from overfitting the training data. And I will just say that the proof idea is to show that if that for every network which has a large number of linear regions, then we can show that it must violate some requirement from the KKT conditions. Okay, so this was the result about the implicit bias. Now I will state very informally the result about the generalization. So basically, we show that under some assumptions on the input distribution and on the network widths and on the initialization, then with high probability over the initialization and the size of the data set, there exists some time t such that a gradient flow reaches a small training loss. Now I will say that the assumptions here about the input distributions and its distribution and the network widths are mild, and the assumption about the initialization scale is a bit non-standard, because we assume that the initialization scale of the first layer is very large and the initialization scale in the second layer is very small. So this is the only non-standard assumption that we make here, and we need to make it for technical reasons.
Can I quickly ask, just for clarification, which one do you call the first and which one the second layer? The inner and outer layer might be.
The inner is the first and the outer is the second.
So the inner layer is very small and the outer layer.
The inner is large and the outer is small.
Okay, so the outer layer moves much faster than the inner layer, kind of.
Yeah.
Okay. Yeah. Thank you.
Yeah, so we need it for technical reasons because we want the first stage in the optimization to be in a lazy regime. And then once we reach a small loss, then the implicit bias will take us to a good solution. But we need this assumption for the first stage of the analysis. Yeah, okay. So now that we have this result about the optimization and also the result about the implicit bias, we can combine them and conclude that under these assumptions that I discussed, with high probability, gradient flow converges in direction to a network with a small number of linear regions that also generalize as well. So it is guaranteed to learn for this assumption about the initialization. The gradient flow is guaranteed to learn successfully the teacher network.
I have a question. Or
yeah.
Just thinking essentially the same question as before, related is if you initialize with these very large first weights and small next ones, it means that you will be very far from being at a KKT point, right? Because to be at a KKT point, you kind of need this balancedness as a property.
Sure. Mm-hmm.
So I guess you don't know exactly how long it will take to actually converge to the KKT.
Right.
Probability taking such an initialization means that it will take even longer than.
Yeah. So the result is an asymptotic result.
Okay.
Consider the time which goes to infinity.
Mm-hmm.
And it is a good question, how long will it take to reach, to get close enough to such KKT point?
Yeah.
We don't know to answer this question. We just know that asymptotically, we will converge to the KKT point.
Okay.
Yeah, okay. I will just briefly mention that there are quite a few prior works that also considered univariate value networks in different settings. But since the settings in these other results are different, none of these other results imply the results that I discussed. So I will not get into all the settings of the different of works. Okay, now I will move to the second part, which discusses a reconstruction of training data from trained neural networks. So it is commonly believed that in some sense, neural networks tend to memorize training data. For example, we can see it in this XKCD comics. I will give you a minute to read it. Yeah, so this comics is funny, but it actually describes a real issue about training neural networks. In this case, this comics considers a language model which is trained to complete sentences, and therefore it can be used by an adversary to leak information from the training data. So in this case, it is a generative model which can complete sentences. And therefore, getting information about the training data is relatively easy. And we will consider neural network classifiers we will consider binary classification. And we want to understand whether this kind of attack is also possible in classifiers. So we ask two main questions. First, are the specific training samples encoded in the parameters of the trained classifier? Okay, so we want to understand whether neural networks memorize in some way training data. And then if the answer for this question is yes, then the next question would be, can we somehow recover these training examples or recover information about this training data from the trained network? And we will show that at least in some settings, the answer is yes. And we will use the implicit bias in order to show it. Now, I can see two main motivations for studying the ability to reconstruct training data from trained networks. The first motivation is that it can help us better understand representation learning and memorization, because if we can recover training data from a trained network, then it means that the data is somehow encoded in the network, which can help us better understand the representations learned by the network. So this is one motivation, to better understand representation learning. The second motivation is related to privacy, because if it is possible to reconstruct training data, then it might be a serious privacy issue, because if, for example, the model runs on some medical device and it was trained with sensitive medical data, then we don't want some adversary with access to the medical device to be able to reconstruct the sensitive training data. So these are the main motivations. And before I describe our approach to construct training data, I will show one result. What we see here is we trained a neural network with 50 examples from CFAR. In this case, the network is an MLP with 2 hidden layers of width 1000. And on the top, we see reconstructions that we see images that we reconstructed from this trained model. And on the bottom, we see the actual images from CFAR that correspond to the reconstructions. So it is easy to see that in this case, we are able to have many high quality reconstructions from this trained network. Okay, so how does our approach work? Recall that we have these KKT conditions, and we know that gradient flow converges to a direction that satisfies these conditions. So when we want to reconstruct training data, we have a trained network. So we know theta, we know the parameters of the trained network, and we want to find a data set such that these equations will hold. So we want to find xi's and yi's and also lambda i's, because these equations also have these lambda i's. So we want to find a data set and these lambda i's such that these equations will hold. And then we hope that if we find some data set that will satisfy these equations with respect to the observed theta, we hope that the examples in this data set will indeed be similar to the actual examples from the trained data set. Okay, so why would we even think that these equations can give us enough information to be able to obtain information about the training data? So I will give an intuition. It's not a formal statement, but this is the intuition that we had, which made us believe that maybe it can be possible. So if we observe equation number 1 here, then equation number 1 is in fact a set of equalities, such that the number of equalities is the dimension of theta. And we want to find the examples. So if we denote the size of the dataset by n and the dimension of the inputs by d, then the number of real variables that we want to find is something like nd, is O of nd. Okay, so we have roughly nd real variables to find, and we have a number of qualities, which is the dimension of theta, and we will denote it by p. And if the network is over-parameterized, then it means that p might be larger than nd. Okay, so we might have much more equations than variables that we want to find. So it makes us believe that maybe it can give us enough information to be able to find these variables. Now, of course, it's not a formal statement because these equations are nonlinear and there are many dependencies between these equations. So it doesn't. We don't have a formal guarantee about the ability to construct training data, but only this intuition about the fact that the more over-parameterization we have, the more information we have about the training data set. Okay, and also another thing that I want to note is that with this approach, we can only recover inputs that are on the margin. Okay, why is this the case? Because if we observe equation number 3, then it says that if the example is not exactly on the margin, then the corresponding lambda I is 0. And if this lambda I is 0, then it does not contribute to the sum which appears in the equation number 1. Okay, so with our approach, we can only hope to recover examples which are on the margin. But as we will see, there are usually many examples on the margin. Any questions about the approach? I will give a bit more details. So usually we don't know n. N is the size of the data set. And we usually don't know it because we just have a trained network and we don't have these details about the training data set. But what we do, we don't really have to know n. What we show is that it is enough to have an upper bound on n. Okay, so we define m, which is at least 2n. We just need this upper bound. And then we will find a data set of size m, which solves the KKT equations. And if there is a solution to these equations with a data set of size n, which we know that there is a solution with a data set of size n, and therefore there is also a solution with a data set of this larger data set of size m. Okay, so this is one trick to avoid knowing n in advance. And also this trick allows us to avoid optimizing on the labels yi's, because we can fix the first half of the examples in the data set that we reconstruct. We can fix the first half to be +1 and the second half to be -1. And then we don't need to optimize over the yi's, we just need to look for the xi's and the lambda i's. Okay, I hope it makes sense. And then in order to actually solve these equations, we do it using gradient methods. So we define these objectives. The main objective is called L stationary. It corresponds to equation number 1 here, which is called the stationarity condition. So this L stationary gets a value of 0 if theta equals to this sum, which is exactly equation number 1 here. Okay, so we minimize this objective in order to find a solution to equation number 1. So this is L stationary. The second objective, L lambda, just requires that all the lambda i's are non-negative, because this is also a requirement in the KKT conditions, that the lambda i's are non-negative. And finally, our main objective that we optimize over is L reconstruct, which consists of 3 parts: L stationary, L lambda, and possibly L prior, which can be used if we want to use some prior knowledge on the data set. In our case, we didn't really use some significant prior knowledge. The only prior knowledge that we used is the fact that the values of each pixel is between, the values are between 0 and 1. So we didn't really use some strong prior knowledge, and perhaps it can be a direction for future works to try to use stronger priors in order to maybe improve the quality of the reconstructions, or to show reconstructions for larger data sets. Okay. Also, another important thing to note is that this objective L stationary is non-continuous because it contains this sum, and in the sum we have this gradient of phi, the gradient with respect to the theta of phi. Now, phi is a ReLU network, and the derivative of ReLU is a step function, which is non-continuous, and it is also constant everywhere. So when trying to optimize over such a function, it's a problematic thing to do it with gradient methods. So in order to overcome this issue, what we do is to replace the derivative of the ReLU with a sigmoid. So we approximate this step function, which is the derivative of ReLU, by a sigmoid, which is sufficiently smooth in order to allow us optimization over this objective. Okay, now let's see a few results. Here we see a reconstruction from a network that was trained on 500 examples from MNIST. In this case, the network has two hidden layers of width 1000. And since we consider binary classification, and MNIST is a multi-class classification task, then we labeled MNIST according to even versus odd. And we trained the network and reached test accuracy of 88%. And then we used the approach in order to reconstruct the training data. And in this figure, we see in rows number 1, 3, and 5 the reconstructions. And in the rows below them, we see the actual real images from MNIST. And as we can see, we have many high-quality reconstructions. An important thing that I want to mention is that our training of the neural network is standard, except for one thing. When we trained the network, we started gradient descent, or SGD, with a small initialization. So we didn't use the standard scale of initialization, which is used in PyTorch, but instead we used a smaller scale of initialization. And the reason is that we have observed that when using small initialization, we get higher quality of reconstructions. And I believe that the reason for it is that when starting from a small initialization, gradient descent converges faster to the direction of the KKT point. And therefore, in the trained network, we get a network which is closer to being a KKT point, and therefore our approach works better. Now, if we try it with the standard initialization, then we're still able to get some reconstructions, but the quality of reconstructions is much lower, and the size of the data sets in which we were able to show reconstructions was much smaller. So it seems like an important factor, and it's also an interesting question of whether we can show these kind of high quality reconstructions also with standard initializations. Okay, now this is the same thing, but with CIFAR. Again, the dataset has 500 examples from CIFAR, and we trained the network with the same architecture and also with the small initialization. And here the labels are animals versus vehicles. So we trained the network and we reached test accuracy of 77.6%. And then we reconstructed the training data. So again, in rows number 1, 3, and 5, we see the reconstructions, and below it we see the actual images from CIFAR. And also here we see many high-quality reconstructions. Okay. I mentioned that with our approach, we can only hope to reconstruct examples that are exactly on the margin. So in this plot, we have a demonstration of this claim. What we see here, every blue point corresponds to an example from CIFAR. In this case, we have 500 examples from CIFAR, so n equals 500. And the x-axis corresponds to the output of the network. Okay, so the points which are closest to 0 are the points which are on the margin. And then the y-axis corresponds to the quality of reconstruction. It is measured by something called SSIM, but the technical details are not very important. What we need to know is that the y-axis is the quality, corresponds roughly to the quality of reconstruction. And we can think about points which are higher than 0.4 as good reconstructions, and points below it as bad reconstructions, basically. So what we can see here is that we were able to reconstruct only examples that are exactly on the margin. And also we can see that there are many examples on the margin. So the set of examples, the potential set of examples for reconstruction in this case is quite large. Then we did the same thing with different sizes of data sets and different architectures. So on the top, we see the same plot, but with different values of n, different sizes of data sets. And in all cases, we see that we reconstructed only examples on the margin, but also we can see that as we increase n, as we increase the size of the data set, then the quality of reconstructions gets lower. So for 1,000 images, we were still able to get good reconstructions. But as we increase it more, then the quality gets lower. And of course, it is a challenge to be able to show better results for larger values of n. Now, in the bottom row, we see different architectures. So we tried fully connected networks with different widths and depths. And in all cases, we were able to show reconstructions. And also, we tried it with networks which are non-homogeneous in the sense that there are bias terms in all layers. Recall that I said that in order for a network to be homogeneous, we can have bias terms only in the first hidden layer. But here we also tried it with a network which is non-homogeneous, and still were able to show good reconstructions. So it suggests that even in settings which are beyond the scope of the theoretical theorem, maybe it can be possible to still get reconstructions. Okay, any questions about the reconstructions? Okay. So I will mention a few related privacy attacks on training data. First, there is this family of attacks, which is called model inversion. In these attacks, the adversary infers class representatives given a model. So basically, what the attacker does in this attack, the attacker tries to find an input that maximizes the output that corresponds to some class. And then by doing it, the attacker hopes that this input, which maximizes the relevant output, will be some kind of representative for the considered class. So the attacker hopes to get information about the classes that the network learned. But in this case, the attacker does not get actual training data from the training data set. Sorry for the noise. A second family of attacks is what I discussed in the XKCD comics. So there are serious works about this kind of attacks, which show that for language models, we can use the fact that these models can complete sentences in order to leak information from the training data set. Another kind of attacks is called membership inference. In this case, the objective of the adversary is to determine whether a given data point was in the training data set. So in this case, the adversary has some guess, some suspect of a data point, and the attacker wants to find out whether this guess was in the training data set or wasn't. And the attacker tries to do it by using the output vector from the network, because the idea is that the network behaves a bit differently for examples that were in the training data. So by observing the output, the prediction vector which is the output of the network, the attacker tries to guess or to determine whether this example was in the training data, and the attacker does it by training a neural network for this task. But of course, a limitation of these attacks is that the attacker must have a guess about a data point. So we cannot just guess all the possible images. Okay, there are also attacks on federated learning. The setting in federated learning is different from ours, but the techniques are somewhat related. In these attacks, in federated learning, the clients send to the server the gradient of the empirical loss with respect to some batch of training data. And then the attacker tries to use this observed gradient that is sent to the server in order to find a batch of training data that will correspond to this observed gradient. Finally, I will say that the ability to obtain information about the training data is also the main motivation behind differential privacy in deep learning. And this is, of course, a very active research area. Okay. I will move to the last part, which is about adversarial robustness. So as I suppose that you know, an adversarial example for a given neural network and input is a small perturbation, such that if we add this small perturbation to the input, we get another input which looks to humans exactly similar to the original input, but now the neural network classifies it differently. For example, here we see an image of a duck, and then we add a small perturbation which looks like a random noise, and we get an image which looks exactly similar to the original image, but now the network classifies it as a horse and not as a duck. Now, empirically, it is well known that neural networks are highly susceptible to such adversarial examples, but it is not well understood why this is the case. And the interesting question is to understand theoretically why neural networks are so susceptible to adversarial examples. So one line of works that tries to understand theoretically the reason behind the existence of adversarial examples considered random neural networks. They showed that for every input, adversarial examples exist with high probability in networks with random weights. So it means that if we choose a random network by choosing each weight IAD from Gaussian distribution, then with high probability, we will get a network which is non-robust. And it means that in some sense, most neural networks are non-robust, or that it also means that at the initialization of gradient descent, since we initialize gradient descent with a random network, then at the initialization, we start with a non-robust network. But of course, trained networks are not random, and properties that hold in random networks do not necessarily hold in trained networks. So we ask whether we can use the known results on the implicit bias in order to better understand robustness. And since we know that there is this bias towards margin maximization, then we can ask whether margin maximization is good for robustness or bad for robustness. Now, in the case of linear predictors, it is well known, it was shown by Surduri et al. That gradient methods maximize the margin. So gradient flow converges to the direction of the max margin solution. And in the case of linear predictors, maximizing the margin is equivalent to maximizing the distance between the data points and the decision boundary, which is exactly what we want when we consider robustness. So it seems that margin maximization is good for robustness if we consider linear predictors. And the question is whether this intuition also applies to neural networks. So we show the following theorem. Consider a data set such that all the examples are on the sphere of radius square root d. It corresponds to the case where each coordinate in these examples is of size O of 1. So we have m such examples. And we suppose that all of these xi's, all of these examples are nearly orthogonal, and that m is not too large. I will define what it means to be nearly orthogonal and not too large in the next slide. And under these assumptions, we show the following. We show two things. First, we show that there exists a Rayleigh network of depth 2 that requires perturbations of size omega of square root d in order to flip the signs of the examples in the training data set. It means that there exists a robust solution. Note that since the examples are on the sphere of radius square root d, then the distance between every pair of examples is O of square root d. And therefore, it is clear that with perturbation of size O of square root d, we can flip the labels of all examples. So the best that we can hope for is to have perturbations of size O of square root d. And the first part of the theorem says that it is possible. So there are robust networks that can classify the data. In the second part, we show that gradient flow will not converge to such networks. More exactly, what we show is that for all depth 2 networks that gradient flow might converge to, we can flip the sign of all labels in the data set with a perturbation of size much smaller than square root d. Okay, so gradient flow, although there are robust networks, gradient flow will not converge to such networks. And in order to show it, since we know that gradient flow converges to KKT points, then in order to show this second part, we show that every KKT point of the max margin problem is non-robust. Okay, so the theorem tries to give, at least in this simple setting, it gives an explanation for why we see in practice, or at least in this setting, why we see non-robust networks, while there exist also robust networks that can classify the data set. So a bit more formally, okay, and also note that as we already discussed, we only care about the direction of theta and not the scale, because only the direction of theta affects the robustness, since the scale only changes the scale of the output. So it does not change the sign, and therefore, if we have an adversarial example for a certain network, then if we multiply the parameters by some constant, the same adversarial perturbation will still be adversarial. So if an example changes the sign for some network with parameters theta, then if we change the parameters to be alpha theta, the same example will still change the sign of the output. So we only care about the direction and not the scale.
Just a brief reminder, it's 4 minutes at the right now.
Yeah, okay, I don't have a lot of slides. So a bit more formally, the assumption is that M is at most O of D over the maximal inner product between two examples. And under this assumption, we show that every KKT point, if we consider perturbations in the direction of this vector Z, which is given here, then it suffices to have a perturbation of size at most roughly a square root of D over M. And for example, if the inputs are orthogonal and we have D inputs, then if we plug in these values, we get that a perturbation of size O of 1 suffices to change the signs, which is of course much smaller than square root D. And if we consider the case where the examples are drawn from the uniform distribution on the sphere of radius square root D, and we have roughly square root D examples, then we get that the size of the perturbation is roughly D to the 1 over 4, which is again much smaller than square root D. Okay, so even for random examples drawn from the sphere, we can see that gradient flow will converge to a non-robust network and not to a robust network. And also, one thing to note is that the results do not depend on the width of the network. So it doesn't matter whether the network is very wide or very narrow. It is still guaranteed not to converge to a robust solution. We skip these two and just conclude. So in the first part, we saw an example where we can use the implicit bias in order to expand generalization. In the case of univariate Rayleigh networks. And as I said it in the beginning, understanding generalization is the main motivation. It is usually the main motivation behind the study of implicit bias. But then in the two other parts, we used the results on the implicit bias in order to show things which are not directly related to generalization. In the second part, we considered reconstruction of training data, and in the third part, we considered adversarial robustness. So although the main motivation is usually generalization, we used these results to show things, to show other aspects of deep learning. And I think it might be also a possible direction for other works to try to use these results, not just to understand generalization, but also to understand other aspects of deep learning.